In this video, we're going to go through section 6.3, which is on finding volumes by the method of integration with cylindrical shells. And so in the previous section, we developed the method of integration for finding volumes, the more general method. So you could consider this the main method of integration to find volumes is what we developed in the previous section. And when I say method, what I'm referring to is what we defined to be the individual pieces that we broke up the volume into. And so again, just remember, if you're trying to develop an integral for something on your own, so you can't reference it in a textbook, the idea is you have a quantity, some quantity, could be area, volume, whatever. You have a quantity that you're trying to solve for, and your thoughts are that you can solve for this quantity by breaking that quantity up into pieces and then summing those pieces, in which case you'll be integrating. That's the process of integration. Now, what you can think about is that if you're going to be breaking up a quantity that you're trying to solve for into pieces and then summing those pieces, then those individual pieces are going to be the same type as the main quantity you're solving for. So if you're integrating to find an area, then you're going to be breaking up that area into little areas. If you're trying to find a volume, then you're going to be breaking up that volume into little volumes and summing those volumes. Okay, and so the method of integration that we developed in the previous section, the main volume integration method, was based on right cylinder pieces. We broke up the volume into little right cylinders. A right cylinder was just you have two bases. Those bases have the same area, the same shape of area. These areas are planar, and those two bases they're parallel planes and separated from each other by a distance. That separation distance is h. And the right cylinder is formed by connecting those two areas by lines that are at all points of those areas by lines that are perpendicular to those planes. That's when you have a right cylinder. But again, the shape of the areas can be absolutely anything. And the volume of any right cylinder is just the area of either base, it's the same base shape, times the height. That's the volume. And so in the previous section, the idea was that the individual pieces were at any position along you can think about the length of the volume of the body. You can think about a plane that goes through that X point that you're at along the body. That plane is perpendicular to the X-axis, or the independent variable axis, and it cuts through the solid. And that cut results in a cross-section, an area. And so you find whatever that area is, the area of that cross-section at the position X that you're at, and then multiply it by delta X. And so you've got this area of a cross-section, and then a little delta X. Right? There's the delta X. That's exactly what a right cylinder is. And so you take the limit as the number of those elements goes to infinity, which means that you integrate from the back end of the solid to the front end of the solid, measured with respect to the independent variable, AX dx. That's the volume, by the volume determined by breaking up the solid into little right cylinder pieces. Okay, and we went through the whole process of how they developed the integral, and in general for any solid, and how they defined what the individual pieces were going to be. What they were going to break up the solid into. Then they carefully defined all of the variable terms associated with that defining one of those pieces, and then when that was carefully defined, the main step was then you break up the solid into like 5 of those pieces and see, okay, is it approaching the shape that we're looking for? Then you break it up into like 20, 30 pieces, a large number of pieces, and you see, is it converging to the shape that we're looking for? And if you see that it is converging, then you can say, okay, well, we can turn this sum into an integral. Okay, so Now, what we're going to do in this section is we're going to develop another integration technique for finding volumes. And this technique is just going to be easier to use in some circumstances. Now, I do want to point out that, so in the previous section, the right cylinder method, there was a special case where we used this to find solids of revolution. But it's not like the right cylinder method was restricted to solids of revolution. We worked example problems that had nothing to do with solids of revolution. So it wasn't restricted there, but it could be applied for the case of solids of revolution. The method we're developing here, the method of cylindrical shells, is just for solids of revolution. It's an alternate method if you have a solids of revolution problem that you're trying to use the, in that case, they call it the washer method. So they call it the washer method because, so yeah, you have a right cylinder, but if you have like for a solid of revolution, the cross section is going to be circular. That's by the nature of solid of revolution. So for the solid of revolution problem, the cross section is circular, and you'll either have a disc or a washer. So you'll either the individual pieces will either be just like a disc, or it'll be a washer. If you're using the right cylinder method, they call it, they talk about discs and washers, right? So if it doesn't have a hole in it, it's called a disc. If it has a hole in it, it's called a washer. And these are the pieces. So if we come here, they're trying to use they're trying to find the volume of this solid of revolution. Well, this is not a disc or a washer, right? But you could still potentially use the disc or washer method here. You break it up into little discs. It'd be washers here. You break it up into little washers, and you'd sum all of those washers to get this volume. So again, for solids of revolution, in the previous section, we used this disc and washer method, but still, it's still like the right cylinder method. This is the delta X. This is the delta X. You've got a cross-sectional area it's circular for the solids of revolution times a delta X. So it's like that right cylinder method that they just call the disc and washer method for the case of solids of revolution. But sometimes using this method to find volumes of solids of revolution it's not that easy to do. It's complicated. And so this is another method. We're going to develop another method that you can use to find the volume of a solid of revolution in this section. And so another method means we're going to define a new element that we're going to break up the solid into. That's not the right cylinder. That's not that disc or washer. Okay? And we're going to need to go through the whole process of setting up this integral. So we're going to have to clearly define with variables in a coordinate system what this element is, and then check and break up a volume into a number of these elements and make sure it's converging as those elements increase. So just as we go through this, just focus on the process that we're using to define an integral, to obtain a quantity that we want. So it says, some volume problems are very difficult to handle by the methods of the preceding section. For instance, let's consider the problem of finding the volume of the solid obtained by rotating about the y-axis, the region bounded by y is equal to 2x squared minus x cubed, and y is equal to 0. So here's the region bounded by 2x squared minus x cubed. This is 2x squared minus x cubed. And here's y is equal to 0. And they want to rotate this region about the y-axis. And so using the right cylinder method, which in this case would be the washer method, what we would do was the independent variable we would treat as y here. We would get x as a function of y, so we can get these distances, and then you would find the cross-sectional area as a function of y. And how would you do that? It would be, so this would be r outer, this would be r inner, and so you do r outer squared minus r inner squared times pi. And that would give you the cross-sectional area for each point y, and then you'd multiply that by delta x. And there's your, in this case, it would be a washer. That's how we found solids of revolution in the previous section. But it's saying here, But to compute the inner radius and the outer radius of the washer, we'd have to solve the cubic equation, y is equal to 2x squared minus x cubed for x in terms of y. That's not easy. Yeah, so you have to, you need to get x as a function of y. That's the key, because you're solving for, y is the independent variable, so you want to plug in y and get x. Plug in y, get x. Get this outer radius and inner radius. But they're saying that it's difficult in this case to solve this equation for x, or for y, for x in terms of y. And so it says, fortunately, we can use another method called the method of cylindrical shells. It's easier to use in such a case. So what we're going to do is, instead of these right cylinders pieces, we're going to instead break the volume up into these shells. Now, this is technically still a right cylinder. It's a right cylinder with circular bases, but you'll see the way we're defining this, it's more of a, it's different. It's a different, the way it's set up is different than a right cylinder. With a right cylinder, you've got a cross-sectional area and then a thickness. This, you'll see it's set up a little different. And because these elements are different than what we did in the previous section, we're going to have to set this up from scratch. So, okay. Here's the element. It's a cylindrical shell with inner radius R1, outer radius R2, and height H. So delta R is R2 minus R1, and then just R is the midpoint between R2 and R1, that radius. Okay. It's the volume of this shell is calculated by subtracting the volume V1 of the inner cylinder from the volume V2 of the outer cylinder. So V2 minus V1, V2 is pi R2 squared H, right? Minus pi R1 squared H, which they write as pi R2 squared minus R1 squared H. Okay, now this is the difference of two squares, so they split it up like this. Pi times R2 plus R1 times R2 minus R1 times H. And then they write it this way. They make this 2 pi and then do R2 plus R1 divided by 2, which is that average radius, that radius of the midpoint of the thickness, times H times R2 minus R1. So delta R is the thickness of the shell, right? This R, just R, is that average radius. And so the formula then of a cylindrical shell you can write as, this makes it more intuitive, 2 pi RH delta R. And this is intuitive because what you do is you say, like whenever you're just getting the volume of a solid right cylinder, you just do pi r squared H, right? Well, they're saying that if you're going to do a shell, the volume of a shell, you can look at it like you do 2 pi r, which is the circumference of this average radius, this mid-plane radius of the two of R2 and R1, of R2 and R1. So you do 2 pi r to get that circumference. Then you do H times H, so that's like a surface area. Then you do the thickness. So it's like an intuitive way to think about the volume of a cylindrical shell. Okay, so that's the element that we're thinking about breaking up these solids of revolution into and summing those elements to get the volume. All right, and we can see the general formula for the volume of a cylindrical shell there. It says, okay, now let S be the solid obtained by rotating about the y-axis the region bounded by. So what they're doing here is, to set up the integral, they're defining a general scenario here. Just a general circumstance where you've got this area bounded by this curve here in the x-axis in A and B. The lines x is equal to A and x is equal to B. Now, this isn't completely general, but it's a start. It's kind of like when we found areas between curves, we started with a certain case of just the one curve is greater than or equal to the other curve. Or even that for just general areas under curves, we started with this case. The curve is positive, and you're finding the area between the curve and the x-axis, and then we expand it out from there. So they're just starting with this case here where the curve is positive. You've got, and it's you're revolving the area between the curve and the area bounded by the curve, these lines x is equal to a and x is equal to b, and the x-axis about the y-axis. Okay, and so, all right, so we want to let's see if we can define the integral for this. And so, okay, what we're gonna do is we're gonna break this up into these cylindrical shells. And so if you come here, the next thing they do is they draw one of these shells relative. Here's the case we're trying to solve for in general, this volume here. So now we're going to put one of our elements into this picture. That's the first step. So you first define what your element is going to be, and also how to calculate like the quantity of interest for that element, which would be the volume. Then you set up a case, a general case, and it could be the most general, or you could be starting with something that's not the most general, but it's still, it's still general here, right? It's a general function f of x. And now you want to go ahead and get a picture of putting one of your elements into that general case. And so we're going to be dividing the independent variable from a to b into n subintervals. And they're going to have endpoints xi minus 1 and xi just like always, right? The right endpoint is xi equal with delta x. And what we're going to do here is we actually want to evaluate the function at the midpoint, because that's part of the way to calculate the volume. So this is a special case where we're not actually going to want to evaluate our function at any point within the interval, because actually our volume formula needs to be at the midpoint. So this x bar I is the midpoint of the ith subinterval. All right, so if the rectangle with base delta x and the height of the rectangle is a function evaluated at the midpoint, is rotated about the y-axis, and the function is this function, is f of x, right? So you've got the delta x times the function evaluated at the midpoint, right? So there's this rectangle. If you rotate that about the y-axis, then the result is a cylindrical shell with average radius x bar I and height, the function evaluated at x bar I, and thickness is delta x. You see? So if we come here, we have the average radius is x bar I. The height is f of x. So we're going to use, this is the average radius, r. That's x bar I. The height is the function evaluated at x bar I, and delta r is delta x. You see? So the volume of an individual element is that 2 pi x bar I, the function evaluated at x bar I, delta x. And you can clearly see you can get any of these volume elements from A to B. This is clearly defined all the way from A to B. You can get any of these. You can get a unique cylindrical shell element with its corresponding volume from x is equal to A to B using this function. Okay, so now we've clearly defined our volume element so we set up a general integration case, and we've clearly defined the volume element for any x position from along the interval from A to B. So next what they do is they draw like 5 of these pieces. We break up the interval into like 5 of these pieces, and you get a sense for this. Okay, actually what they also do is they actually draw out this perfect solid, like this is the actual solid of revolution. So this is what we're trying to find the volume of right here, right? You revolve this around the y-axis, there it is. So now they break it up into 5 pieces and just get a sense for, okay, it looks like it's approaching this shape, so it looks good. But then an important step when you're trying to set up an integral is what they do is they break it up into as many pieces as is reasonable, to where you can still kind of see and count the pieces. Like, they put like 30 pieces. And when you do this, you should clearly see that it is converging towards your desired shape. I want to find an example. I've seen examples where, you might think, well, it'll always converge. Well, no, you might set up an element and you think this element is going to work to do this integration. And then whenever you apply like 30 of those elements, it's clearly not converging. Like if you apply, like here, it's kind of hard to see if it is converging or not. It looks like it is, but when you apply like over 20 elements, then it's going to be very clear if it's converging or not. And here it clearly is. So when they see this, that it is converging, then they say, okay, well, we can turn this into an integral. And so, well, what they actually did do, but I guess before they did these steps of breaking it up, they wrote this as a Riemann sum. So if we come here, well, they take this formula for the volume of an individual element, and they write it as a Riemann sum. So the sum from I is equal to 1 to n of VI, and there we go. So now you can plug in 5 or 20, and so if we come back, that's what it is here. This is the Riemann sum with V of 5. This is V of 20 or whatever this is. And so when they see that, okay, it clearly converges once if you start putting a lot of those elements and you let n get pretty high, then they say, okay, you come to the conclusion that we can turn this into an integral. That this element that we chose, this piece type that we chose to break up our quantity we're trying to solve for into, it works. And so we can make an integral with it. And so all they do is they take the limit as n approaches infinity of the Riemann sum. And we've talked about, so now this is the integral, but we want to write this in integral notation. And so this here is the elongated s, the infinite sum, elongated s. You put the limits of integration. You just put this as a function here. And it is, it's interesting to note that because we're taking the limit as n approaches infinity, it didn't matter if it did choose the left or the right endpoints. It would all converge to the same value. But still, to be technically correct, you want to define it this way because to make it correct per the definition of the volume of a cylindrical shell. But as n goes to okay, so why would you want to define it this way? Because if we come back, so with previous problems, if you were doing an approximation, then you could choose to use the left endpoint method or the right endpoint method. But here, you don't choose left. If you're doing an approximation, you don't choose left endpoint or right endpoint. You need to use the midpoint because that's based on the definition of the volume of the cylindrical shell. But it's just interesting that when you take the limit as n approaches infinity, it technically doesn't matter. You could set up the actual shells to where the height or what you use to get 2 pi r, that circumference, you could have chosen the left endpoint to calculate 2 pi r or the right endpoint. And as n goes to infinity, it would all still converge to the same value because the elements are so small. As n goes to infinity, the delta r is getting tiny. The delta x is the delta r. Okay. So it's just interesting to think about that. But so you just put the function. So you put 2 pi x f of x, and then as n goes to infinity, delta x gets infinitesimally small, so we write that as dx. Okay, and so there's the volume of a solid of revolution. So the volume of a solid obtained by, so it's a solid of revolution rotating about, they say the y-axis here, but obviously you could rotate about any axis. The region under, a region bound by some curve from A to B is, and here it is. Right, and so, you don't have to use x as the independent variable, but this is talking about a solid of revolution. You can now use this method, and it doesn't matter what the independent variable is, as long as it's a solid of revolution. You could use this method. You could break the volume up into cylindrical shells or discs or washers, like we did in the previous section. All right, so it says the best way to remember Formula 2 is to think of a typical shell, cut and flattened as in figure 5 with radius x, circumference 2 pi x, height f of x, and thickness delta x. So yeah, when you think about the volume, another way to look at the volume of this is you have some bar with length 2 pi x, like you cut and flatten this out, and the length is 2 pi x, the thickness is delta x, and the height is f of x. But that's not very intuitive to me because you cut and flattened it out with the average radius, but that's one way to look at how you're calculating this volume. You can cut this cylindrical shell and lay it out flat and get a rectangular bar here. And, this is 2 pi x is that average radius, that midpoint between the R1 and R2. So this is the circumference 2 pi x, right? Times delta x times f of x. That's the cylindrical shell volume. It says this type of reasoning will be helpful in other situations, such as when we rotate about lines other than the y-axis. Okay, so yeah, keep this idea in mind of how you can think about the volume of a cylindrical shell this way. By you cut the shell and flatten it out into a bar, a rectangular bar. All right, so now they come back to the original example, that this 2x squared minus x cubed, which would be difficult to solve using the washer method, because it'd be hard to solve for x as a function of y. And so what they do is, so how do you set this up? Well, the delta x in this case is the thickness of the shell, right? You see? And so what's changed is now the function value we're going to be using in the integral, we don't need to find x as a function of y. The function value is the height in this case, the height of the shell. The radius is just x. So you have the volume is 2 pi x times the function evaluated at x times delta x. And that's what you're integrating from 0 to 2. And so now it's a simple integral. Done. It can be verified that the shell method gives the same answer as the slicing method, as the washer method. All right, so it says, well, yeah, here's the solid. So weird looking solid, but yeah, you broke this up into shells, and you integrated out. As opposed to with discs or washers, you would have integrated up like this. Comparing the solution of example 1 with the remarks at the beginning of the section, we see that the method of cylindrical shells is much easier than the washer method for this problem. We did not have to find the coordinates of the local maximum, and we did not have to solve the equation of the curve x in terms of y. However, in other examples, the methods of the preceding section may be easier. So yeah, if we come back here, it was easier to use shells here because, yeah, we didn't have to solve for x as a function of y, but then also, and this wouldn't have been that big of a deal, but if we were using the washer method, we'd have to find what is this local max here to get our upper limit of integration, right? We'd be integrating along the y-axis from 0 to whatever this is. In this case, it was kind of clearly set up. We just went from 0 to 2. So it's saying, though, in this case, shells was easier, but in other scenarios, shells aren't necessarily easier. It just depends. So for a solid revolution, it's which method is easier, the disc washer method or the shell method. It just depends on the problem. All right, find the volume of the solid obtained by rotating about the y-axis, the region between y is equal to x and y is equal to x squared. Okay, so you can see how you could potentially use the disc washer method. It would be the washer method in this case, or the shell method. But we're going to use the shell method, and so in this case, the x is going to be the independent variable, and you'll have 2 pi x times it would be the function evaluated at x, this function evaluated at x minus this function evaluated at x to get the height times delta x. And so that's what they do. And look, it's pretty, quick and easy. All right. As the following example shows, the shell method works just as well if we rotate about the x-axis. We simply have to draw a diagram to identify the radius and height of the shell. Yeah, so we're going to rotate about the x-axis here. And so now we have the shells are turned sideways. We're going to be using the y as the independent variable because the thickness of the shell is delta y. And so we'll have to solve for x as a function of y because the height of the shell is going to be x is equal to 1 minus whatever x is when you plug in, what would it be? 1 minus y squared would be this x value times delta y. And so they do this and they get pi over 2. And, it works pretty well. But they note that we solved this problem using discs in the previous section. And actually the discs method was a little bit easier. I mean, this was pretty easy. And so if we come take a look, so here's that same problem. And so what we just did was we did the shell method, right? And we evaluated it. So, you know, you have, there's y, that's the radius, the y value, the average radius is just whatever y you're at. Then you've got delta y is the thickness, and then this x value minus this x value, which you have to solve for, it would be x is equal to y squared, and that's the height. That's what we just did, but with it would be disks in this case. You put x as the dependent variable or the independent variable, and you've got, and you just find you're finding the area of the cross section at each x point, and so that would be pi times this is the radius, so square root of x squared, and then there's the cross sectional area, and you multiply that times delta x, and you've got the disk, and you integrate that from 0 to 1, and they show that's a little bit easier, you know. But here you get pi over 2. Here you get pi over 2. Okay, last example. Find the volume of the solid obtained by rotating the region bounded by y is equal to x minus x squared and y is equal to 0 about the line x is equal to 2. Okay, so yeah, so we're not going to be rotating about the x or the y axis, but it's the same idea. You're going to be breaking it up into shells. Just like, you know, we did problems where you could use disks or washers for rotating about like a line like y is equal to 3 or x is equal to 2. And so you get, what do you do? Each element, so we're rotating, what is it? Let's come back here. The region bounded by x minus x squared and y is equal to 0 about the line x is equal to 2. So we're rotating this region about x is equal to 2. So we're rotating, okay. So, you know, you could do shells and you'd be integrating, each shell would be like this. Or not shells, that would be washer. You could do a washer. But here they're doing shells, and so you need to get we're integrating, the independent variable is the x, and so the delta x is the thickness of the shell, and then the x coordinate of this relative to x is equal to 2 is the radius. And so that's kind of the tricky part. You have to, we're integrating from 0 to 1, okay? And so for any x as you go, so you're integrating here, here, here. So like for this x value, you know the function is equal to, well, no, for this x value, this is x is equal to, let's say, 0.25. Well, then what you're putting in there is 2 minus x for the radius. See, 2 minus x. So 2 pi times 2 minus x. And then the height is just x minus x squared. And then delta x, and that's the cylindrical shell. You integrate that from 0 to 1. And, you know, something to point out here that we didn't see this in the previous section was how we used the x coordinate as part of the formula for our differential element, the formula for the quantity of the differential element. So like previously for areas, we had the independent variable for areas between curves and even volumes of volumes by the right cylinder method. We had the independent variable delta x, but then everything else was based on the function of x, was based on like the you know, you have y and x, you had delta x, and then everything else that we were multiplying by delta x was based on the function. But here we're actually using the x coordinate as part of the definition of our element. Like we didn't do that before. We didn't have, you know, like the cylindrical shell. We're actually using the actual x coordinate as part of the calculation for the quantity of the differential element. If you think about it, we didn't do that. We haven't done that yet. So you really have got both variables, the function the x variable evaluated at the function, but also the actual x position itself is a variable you can use to define the differential element. Okay, so now this last paragraph talks about when do you use, if you're going to do a solid of revolution, how do you know when to use the disk washer method or the cylindrical shells method? So it says, when computing the volume of a solid of revolution, how do we know whether to use disks or washers or cylindrical shells? There are several considerations to take into account. Is the region more easily described by top and bottom boundary curves of the form y is equal to f of x, or by the left and right boundaries of x is equal to g of y? So what they're saying here is that it's like in that first problem, it was hard to get x as a function of y. And so that's something to consider. Is it difficult to get y as a function of x or x as a function of y? Because that's one of the key differences between cylindrical shells and disks and washers is they operate on the opposite independent variable. So if it's the case where one of these is really hard to get, then choose the method that's more in line with what's easier to obtain. Y is equal to f of x or x is equal to g of y. Okay, which choice is easier to work with? Are the limits of integration easier to find for one variable versus the other? Yeah, so is it the case where it's hard to get the limits of integration based on y is equal to f of x or x is equal to g of y? Or maybe depending on if you're using y is equal to f of x or x is equal to g of y, do you have to use like multiple integrals? You have to separate it into different integrals. Whereas if you used, a certain independent variable, you have one nice clean integral. Then are we able to evaluate the integral we set up with our choice of variables? So yeah, you might set up the integral and it's a complicated integral. You can't even evaluate it. And so you might say, well, let me go to the other independent variable with the method of washers or shells and see if it results in an easier integral. If we decide that one variable is easier to work with than the other, then this dictates which method to use. Draw a sample rectangle in the region corresponding to a cross-section of the solid. The thickness of the rectangle, either delta x or delta y, corresponds to the integration variable. If you imagine the rectangle revolving, it becomes either a disk or a washer, or a shell. So what they're saying here is that you start the problem. One way of looking at this is you start the problem, and all you're looking at, you're not even thinking about disks or washers or shells. You're just thinking about which is easier to set up to get, like in both cases for shells or disks or washers, you're going to have a rectangle in the plane. Before you've revolved, for both techniques, you're going to have a rectangle, right? If you think about it, for both shells or washers or disks, it was always in the plane. You have a rectangle before revolving, and so you're going to the idea is you want to see, okay, which is easiest to set up that rectangle with, which independent variable is easiest to get the limits of integration, to solve for y as a function of x or x as a function of y. Okay, and so then from there you figured out which is the easiest. Now you've got your rectangle, then you see, okay, now revolve it. And it'll be clear, okay, when you've revolved it, you'll either have a disk or a washer, or you'll have a shell. And then you'll just proceed from there. So, all right, so let's work some example problems.